Hi everyone. In this problem, I thought I'll discuss a very simple but an interesting problem which contains both positive and negative feedbacks. But both the positive and negative feedback factors are the same. In that case, how does one guess the output of a system? So here is a simple opamp based circuit where there is both positive, so this is a negative feedback and this is positive feedback, where there are both positive and negative feedbacks, but it turns out the feedback factors are exactly same. It's half in this example. So it's given that this opamp is an ideal opamp with a finite saturating voltage. So its output can't go to infinity. It'll either saturate to plus or minus Vsat. So that's what is shown here. So it's an infinite gain opamp with a saturating nonlinear saturating characteristic. So before we analyze this problem, what we will do, we will look at an equivalent block diagram representation and try to draw some simple conclusions and then apply that to this problem. So shown here is a simple negative feedback block diagram, and you have a forward path gain A, and there are two feedbacks. So one is a negative feedback with a feedback factor beta 1, and another one is a positive feedback with a feedback factor of beta 2. Okay, when both these negative and positive feedbacks are present, we discussed previously in one of the previous lectures, how do we analyze when we have both positive and negative feedbacks, is that we just look for which feedback factor is higher. So if the negative feedback factor, if beta 1 is greater than beta 2, then the overall feedback, the signal which is fed back, will be negative. Okay, so therefore we can say it's a negatively feedback system. Once you know the system is negatively fed back, then you can clearly define what the closed loop gain is. Okay, then you can, once you know the closed loop gain, if you know the input, then you can exactly write what the output is. The next condition is what happens when beta 2 is greater than beta 1. So which is your positive feedback gain is greater than the negative feedback gain. In that case, the system, the control system here will become a positively fed back system. And in that case, even if you apply a small finite input, the output can grow unbounded. So that's the definition of stability. When we define stability, we said, for a finite input or a small input, the output can grow unbounded. The third case, which is of interest to us, is the case when beta 1 becomes exactly equal to beta 2. When both beta 1 and beta 2 become exactly equal, okay, then it looks like as though no signal is fed back. So which means there is no feedback at all. The positive feedback exactly cancels out the negative feedback. So which means there is no signal fed back at all in the first place. So that's what is the problem in our case. Okay, so just to illustrate the third case, so what happens when I have to understand the problem beta 1 equals beta 2, I can simply reduce this negative feedback system into a system with both negative and positive feedback as a simple system with negative feedback with a single feedback beta, where beta is simply given by beta 1 minus beta 2. So I just clubbed these two parts, beta 1 and beta 2. I just added these two parts. All I did was I just put a minus sign here and put a minus here. So you get, when you multiply these two, you'll get a plus. Okay, so then all I did was I just added this path with this path. You get a single beta whose value is beta 1 minus beta 2. Now for this closed loop system, assuming the system is still negatively fed back, I can express the loop gain as a by 1 plus a beta, which is given by a by 1 plus a into beta 1 minus beta 2. Now from this expression, I can mathematically say, okay, if both beta 1 becomes equal to beta 2, then the loop gain simply becomes equal to the open loop gain itself. Okay, it's because beta is 0, so it looks as though there is no negative feedback at all. So that's what I've just shown it here, okay, in a figure. So if I have both negative and positive feedbacks, then the output signal is present. Both of them are fed back to at the input port, and they both exactly cancel out. Okay, so what you're left with is just the forward path gain. So the system behaves like as though it was an open loop system, as though it is an open loop system. So now coming back to this problem, we have to look at, there are three paths here. So what is of interest to us? So this amplifier is nothing but it computes error. So it's like a summing block, and also it amplifies the error. Okay, it's both of them clubbed together. So it's a summer followed by a high gain amplifier. So the gain I can assume, I mean, it's ideal op amp, so it's an infinite gain with a saturating characteristic that looks like this. So what are those three paths? We can just see that as far as the input is concerned, at this terminal I can write V plus and V minus. So V plus is the positive voltage and V minus is the negative input voltage. V plus, there are two signals that are summing together. So you have a resistor and a resistor. So if I have a signal Vi here and a signal V0 here, you're supposed to find the voltage. Let's call this V plus. So you just apply superposition and find that out, so that you get Vi plus V0 by 2. And similarly, V minus is just V0 by 2. Now the actual error measured by this op amp is the difference between the two voltages. That will simply be just Vi by 2 itself. You just subtract these two, it will be Vi by 2. So now what you see here, the actual error measured by this op amp contains no information of V0, which means there is no feedback. That's what this means. Okay, there is no feedback, and the error will simply be equal to Vi by 2 itself. So that's what I've shown here. So I've shown from the input to the positive terminal V plus, the gain is half. Then from output here, Y equals V0, beta here is half. So you get V0 by 2 and minus V0 by 2 on the negative terminal. Okay, so when you add all these, what happens here is the negative and positive feedback paths cancel out. You are left with a system that looks like this. So this 0 here simply represents that both the negative and positive feedback path gains of negative and positive feedback paths voltages have cancelled out. So this I'm going to this is the model for your op amp. It's a summing amplifier followed by a high gain amplifier. So that I'll replace by an op amp. So it just reduces to something like this. It just reduces to an open loop structure that looks like this. Vi followed by a gain of half and followed by an ideal op amp with a saturating nonlinear characteristic. So now you can very easily write what its output is. So if I feed a sinusoid at this input terminal, it gets attenuated by half and fed to a nonlinear amplifier or operational amplifier. When I say nonlinear, I mean the saturating characteristic, ideal op amp with finite saturating voltages. Okay, so then whenever your input goes positive, output goes to plus Vsat. If your input is negative, output goes to minus Vsat. So it will behave like a zero crossing detector. Okay, so that's all. So it's a very small problem. I thought I'll make a series of lectures on